the board or the Google Doc, and perhaps address some of them then, perhaps punt some of them, and then we'll spend a bit of time before dinner trying to organize groups for tomorrow.
Yeah, this is my slide, and this is the other one, and this is
They were displayed.
Okay. Do you what are you in? Do you want to export slides and give them to me, and we can have Li-Ping go for you?
Sure.
Okay, Li-Ping, do you want to go ahead?
Sure. Okay.
I'll send them to you. Well, I'll export them to PDF.
Okay. All right.
Before we start, you said you had one.
Multi-step optimization. Just bounce for 5 minutes. Parameter space that we might actually
Oh, multi-start, you said.
They start from different
Yeah,
nations.
yeah, I think that's a good idea. Okay. Well, good afternoon, everyone. I'm Li-Ping, in case you haven't met me yet. I'm starting my career at UC Davis in the chemistry department. And today I'd like to tell you about the ForceBalance software that I developed in a very quick introduction and how it fits into our open force field effort. So this is the this is the slide, the diagram that I'd like to use to explain what ForceBalance is. Essentially, it is an automated force field optimization software that performs an iterative optimization of force field parameters in a least squares sense. And if you think about this problem, there's a few fundamental components. You read your force field file into an internal representation, and you need to be able to manipulate the parameters in the force field file. And then using this force field file, you need to be able to perform simulations. And ForceBalance itself doesn't run the simulations internally. It calls external simulation codes to do that. That includes interfaces to OpenFF and Amber and Gromax and Tinker and a few others. And then and from these simulations, you can get force field predictions of properties that you can compare to experiment or to ab initio calculations, depending on what the properties that you're interested in. And then you can take differences between your force field predictions and a reference data set that you've gathered by hand and formatted it in a way that ForceBalance can understand. And from there, you can build a least squares objective function. And if you know the first derivatives of your properties, you can actually get a good approximate second derivative of the objective function. And that allows us to use an efficient truss radius Newton-Raphson optimization that will allow us to converge to a local minimum, usually in a small number of iterations, like 10 or less. And so now so it's on GitHub. It's open source. It's a command line program written in Python. I wrote everything in Python 2, but I'm definitely planning to make it Python 3 compatible. And the inputs are just to make things a bit more concrete. That you first give it a force field file, and this can either be plain text or XML, and because different programs take different formats. You also have a data folder, which can include multiple data sets that can go into a single objective function. This can either be ab initio data or experimental data. And there's also an input file containing the settings of the optimization. And then when ForceBalance runs, it produces some outputs. At every optimization cycle, it will give you a folder containing current parameter values and simulation results. It'll produce an output file containing the convergence behavior of the objective function, and at the very end, it'll give you a final optimized parameter file. Here's some of the results and ongoing work that that force balance has been used for. So most recently, I developed the all-atom protein force field called Amber FB15, mainly using ab initio MP2 potential energy surfaces, and this has also been used to develop a phospholipid bilayer model. I'm not the first author on this. A student in BJ Pani's group did this. Force balance has also been used to develop a series of water models. And the reason why there's so many water models here is mainly because once you've got the data set loaded into force balance, it becomes very easy to change the functional form and then test out the quality of fit for different functional forms. So the first such water model that I published is iAmoeba, which is a polarizable point dipole model using the direct approximation. And then following that, I developed some rigid fixed charge models. These are strictly analogous to TIP3P and TIP4P. They just say FB for force balance. And then we applied the same framework to develop other versions of the amoeba force fields, like amoeba 14, which which uses mutual induction, and one called UAmoeba, which is actually a united atom model. More recently, a collaborator has implemented the ability to fit radial distribution functions. This is submitted, not published yet. We've also developed some small molecule, some small molecule Leonard-Jones parameters about 3 years ago, and there's some ongoing coarse-grained protein force field work. And one last note is that I actually used force balance to develop some grids and tensor hypercontraction, which is sort of like, think of this sort of like a basis set, like a quantum chemistry basis set. And so the idea here is that force balance also works on applications that don't have atom types or even force fields. So it doesn't make a lot of constraining assumptions, which hopefully will make it flexible for things we're interested in. Just as a small follow-up on the previous section, I want to show a comparison of simulation results for physical properties of pure water, where if you look at the TIP3P model and the TIP3PFB model, the parameter values are in the bottom left here, okay? And you can see that the parameters change by just a few %, right? These changes really are quite small. Like the biggest change is about 5% in the bond length and the angle, and the non-bonded parameters aren't changing all that much. But the differences in the thermodynamic properties and the kinetic properties are really kind of dramatic. So here are some of the properties that we fitted. In black is the experiment, and this is the density of water as a function of temperature. There's a well-known temperature maximum density at 4 degrees Celsius that none of the 3-point water models are able to get it exactly. Okay, but TIP3PFB does get it a lot closer. You can see the isothermal compressibility and dielectric constant are also significantly improved. And here's some validation properties that we did not fit. And so if you look at the radial distribution function, TIP3P understructures it. Especially the second peak is not as prominent as it should be in the experiment, and TIP3PFB seems to recover a lot of this behavior. And TIP3P is also like too runny of a water model. The diffusion coefficient is too fast, and the shear viscosity is too low. These two properties.
Is the water evaluation part of the force balance, or it's separate?
The data, when you clone the force balance repository, the data for water just comes with it. I just looked it up in the JFIS ChemRef data, and I formatted it as a text file. So you download force balance, you get the data automatically.
Did you use any quantum data?
For so I did, but it didn't help. I got that the error in the ab initio forces was always around 60%, and in general, my experience in water models was that the absolute energies and gradients really cannot be well fitted by a fixed charge model in a gas phase. If you use a flexible polarizable model, the story is very different. But you can get fits that are a lot better. Yeah, so the answer is the ab initio data is in the training set, but I don't think it had a positive impact. Maybe it did, but the quality of fit didn't get better in any case. Yeah. And so
Just a second, so
yeah.
did you use, so how did your PFD work on free-sol hydration-free energies?
I tested hydration-free energies on some of the amino acid side chain analogs from the Ambler force field, and I got that the changes in the hydration-free energies were all quite small, on the order of 0.1 to 0.2 kcal per mole, and things didn't get significantly better or worse.
Do we think that could be a good thing to make sure that things don't get too bad if we're changing based on host-guest interactions, like using the free energies of hydration of host-guest? Of sidechain analogs.
Yeah. So my perspective is that if we move forward together to develop a better water model, that we should include both the free energy data, such as the data that Mike
So the
presented,
host-guest,
as well as the physical properties of water.
the physical properties, and also the sidechain analogs, just to make sure they're not, or would you omit them? You said that they didn't change too much.
They did not change too much. Yeah.
But they might be a guard against
Crazy.
screwing up the Leonard-Jones too much.
Yeah. Yeah, right. Yeah, I agree that like including some targets in ForceBalance like that is sometimes just a guard against overfitting. And you make sure that your parameters are just the best compromise between different things.
Although, I mean, I'm not espousing this view. I'm really not sure, but we did have a discussion earlier about not going to gas phase. for
Yeah.
the-
And
so,
I would normally think that's the case, but
Right.
it's the easiest thing to include
I know,
that would keep us from
I know.
screwing up too much.
Maybe it goes, yeah. I think it's interesting.
But did you write your own scripts to calculate the water properties, or it's part of the, like if I want to use your tool to generate a new water model?
It's right. The procedures to compute properties are part of ForceBalance. So I basically I implement an empty software agnostic procedure to compute the properties, and then so for example for the density I say run an empty simulation and then get me the the time series of volumes for example, and then just take the mass and divide by the volume, and then and the ForceBalance has 3 or 4 interfaces to external simulation softwares where, depending on the MD software that you want to use, it'll call GROMAX or Amber or OpenFF and get you the property that way. So for example, if you want to fit a property that isn't in ForceBalance yet, then it requires implementing that computational procedure. And my hope is that ForceBalance is designed in a way that makes that easy.
But I'm just, with your increase in bond length and your increase in charge, you've got to have an increase in the dipole of about 1% or more.
Yeah.
So that should have a ramification for hydration-free energies of polar species. But you've looked at the amino acid side chains, which have only a few polar guys in them.
Mm-hmm.
But we haven't looked more widely than that yet.
I have.
John put together a free-sol mini, which is like 10 molecules that spans the full dynamic range of hydration-free energies in free-sol roughly. It would be very informative to look at that, since then you get like the most polar thing there.
Yeah, I'm interested, especially since in Mike Gilson's presentation from earlier, Mike, you found a decrease in the binding free energies, a decrease in the binding free energies, and you didn't change the charges or the geometries, you just changed the Leonard-Jones. But it was interesting, the effect of the better water model was to decrease the magnitude of the binding energies, but these changes, I can't see how they could do anything else except increase the magnitude.
Okay, let me, is it possible that this would make the solutes more stable in water and thus weaken the binding?
Yeah, seems like it.
Yes. Yes, I think they would.
It's the polar ones.
Huh. It would be very interesting to see.
Yeah.
I'm pretty interested. Okay, sorry then. Digress.
Thanks for the suggestion. I'm just going to protect myself against a potential future negative result by saying I'm not claiming that this water model will give you more accurate free energies when the solid is parameterized in the Amber workflow,
Mm-hmm.
right? Because this water model was parameterized without any knowledge of Amber parameters other than having tip 3p as the starting point. So I think it's good to have a, to specify what force balance is really doing and what are the human choices that go into this parameterization. So this is just the rough representation of what force balance is doing. The theta in the brackets are the parameters, and then to get the optimized parameters, you're just finding the thetas that minimize this expression, right? And on the left here, you have this expression represents the terms in the objective function, the errors and the least squared errors between the simulated quantities, which is here, compared to the reference quantities here. There's some kind of normalization, and in most cases, the variance of the reference data serves well for that. The W here is the relative weight of the different data sets, and then this term is the regularization or the penalty, where for every where you have again a choice of like a kind of length scale for parameters of different types. This helps to on the one hand, it makes your parameter space unitless and the optimization more well conditioned, but this also allows you to set essentially how much is each kind of parameter allowed to vary. You can think of it sort of as a prior width. So, yeah.
The theta Q0, is that just your initial theta?
Yes. Yeah, that's right. So
What was it?
Initial parameters.
It's like the tip 3p in this case.
yeah, that's right. So so first you choose the input data set and the relative importance of data, right? So the user chooses the relative weights of the data sets. And then also in characterizing the parameter space, you have to choose the starting functional form in which parameters are being optimized. In practice, this is done by taking the force field file that you're going to run simulations with and just adding comments to it that the MD program ignores, but force balance understands. And that allows it to represent the force field file internally and be able to manipulate the individual numbers and write out an edited copy that you can then use to perform simulations with. And the user also chooses rescaling factors for each parameter type when computing the penalty term. So the two, I guess, arrays of numbers that you have to choose are the relative weights and the rescaling factors, right? One of them determines like the weights on your data, and the other one sort of allows parameters to vary by different amounts. And in the case of Amber FB15, we had over 1,000 parameters that were being optimized, and the number of numbers that I had to choose was like 10. So
How is it only 10?
because I choose one B for every parameter type.
Every parameter type, okay, rather
Yeah.
than for every parameter, okay.
Right. And in the iAmoeba project that we worked on together, that model had 17 parameters, but pretty much every one was a different type, so we had to choose 17. But iAmoeba also had a much greater data set. So yeah, and I also had to choose like 2 or 3 different numbers that weighted the different types of ab initio data with respect to each other. And I would argue that that in practice, having to choose these numbers is actually not that terrible because you're going to get big differences in your results if you vary these, the W's and B's by like a factor of 4, right? But if you change them by 5%, they're barely going to impact your results at all. On the other hand, changing the parameters by 5% has a huge impact on your results. So I think that this kind of approach leaves the larger and more qualitative decisions to the user, while the really precise say choices of what the parameter values are, you can leave it to the optimization to figure out for you.
But keeping yourself pinned to previous parameter sets could be problematic. Does that help erase the multiple minimum problem though? Like in the Amber reparameterization, did you start from multiple initial conditions, initial starting points, or end up with multiple solutions in different basins? Because I'm quite sure that at least the left part is not going to be convex, right? But if you add a strong enough harmonic potential, it might make it look like there's a unique minimum.
So I think you could definitely end up with different sets of solutions. I agree. But the goal here, at least my goal is not to find the set of parameters that is the very best.
Yeah.
I just want to find a set that performs well.
Yeah.
And in this case, if you start with the same parameters, you'll end with the same parameters. It's reproducible in that sense. Except when you get the thermodynamic noise. You have to, if there's some thermodynamic property.
So what happens if you didn't have the harmonic constraint to the initial value of the parameters? Does it wander far away?
It depends on the data that you use in the term on the left. So
Because I guess the issue with the harmonic, so this is just like RESP. It's very similar to RESP, or any of these things that we constrain. And I was constrained initially with the harmonic constraint, and the problem was when my charges actually should be really different from zero, I was artificially constraining to zero. So the corresponding problem is when your initial guess is not very good, so you're only allowing yourself basically a small or some kind of a perturbation. So I guess I'm wondering about that. Like, how can we be less constrained by that?
Force
regression.
Yeah, so ForceBalance does have an option for an L1-like penalty, a hyperbolic one, just like the one you did for RESP. I just didn't talk about it.
Okay, but again, we should continue this offline. Sorry.
But yeah, you are sort of tied to the initial values that you started with, and in the projects I've had where I've collaborated with a lot of people tend to feel more comfortable with the final result if the parameters don't go too far away from their physically intuitive values. Yes. Yeah, it is. Yeah, I guess part of the reason is that the parameters are supposed to represent something physical, and we usually have some reasonable guess for what they should be.
So we get to run.
That's not always true, right? But sometimes it is.
So when we run this, we can turn the comfort dial all the way down if we want.
You can, yeah, and maybe if you choose a good enough data set, you don't need the term on the right at all. But I think, for example, if you have if you have two terms that have the same, say, distance dependence, but they're very similar to each other, you can increase one by 1,000 and increase the other one by negative
The
900.
near linear dependency of the design matrix.
Right. Yeah. And in that case, maybe you can never, maybe like you're always going to get some bad behavior if you.
But this is
Okay, that's-
exactly the kind of dependence that John is talking about when you're talking about figuring out what those dependencies are and trying to contain them other ways.
Well,
I
I think
see
it's
what
like
you're
what-
saying. That's what I was trying to control with my restraint with charges is exactly that. So I'm not going to. It's a good method, right?
Mhm.
But what John is talking about is we need to actually find out where we have these dependencies and be able to contain them. Know that they're there and contain them other ways is actually something else. that we
Or
need.
at least characterize them in case they might have some unintended effect outside of the training set.
Well, I think what it does do is that it does greatly diminish the curse dimensionality. So if we find ourselves really stuck wandering around lost in parameter space, this can at least guide you to a result that you can give to your consortium members and say it's better than what we had before.
Right,
Even
which
if it
is
isn't fully optimal.
Yeah.
Yeah, that's sort of
Great
why we went weeping and Bosch.
Yeah.
This will definitely work.
Right. I'm just offering ForceBalance as a practical but imperfect solution to some of the problems we have.
Do you calculate a covariance matrix? You must somewhere along the way.
I've
Because your covariance matrix would exactly tell you when you've got these compensating.
Well, he's got a Hessian, but
Mhm.
the Hessian kind of characterizes, at least locally, linearly, right?
But but if you only do 10 iterations, 5 or 10 iterations, you're not going to get much sampling of your covariance matrix.
Yeah, the Hessian is
So
where.
Yeah.
So do you need the Hessian of all of the properties that you're computing, or only some of them?
No. I just calculate the first derivatives of the properties, and then using the Gauss-Newton approximation, you get an approximate Hessian. But you can also calculate the exact Hessian with finite difference if you want to.
Sorry, you use which approximation to get the Hessian?
It's called the Gauss-Newton approximation. It's like it's something like this. The Hessian of a least squares quantity looks something like it looks something like this.
Which is the gradient.
Yeah, I mean this equation is not exactly right, but
you still have a
essentially
Hessian in there,
is-
right?
Hmm?
You have the Hessian on the right.
Yeah, the Gauss-Newton approximation
Oh!
says this is 0.
I see.
Yeah, and in practice, this has just been pretty effective.
Okay.
That's the outer product.
Yes, yeah. There's the outer product of
Yeah.
the first derivatives of properties. Yeah, and so here are what I think the future directions of force balance could be as part of the Open Force Field Consortium. Well, we do need to bring the code up to date with some of the recommended best practices of the consortium. That means introducing Python 3 compatibility, and I took some initial cracks at this, and this does require some non-trivial code changes. It's not just running 2 to 3. So ideally, I could have the help of somebody who knows Python 3 better than I do. We should change the license if needed. I am completely open to a more permissive license. The main thing is we just need to reinspect all of the code that I included from elsewhere, right? I think about 80% of the code in ForceBalance is written by me, but some 20% of it I incorporated from elsewhere after checking that with the license that it was okay. So we'll have to recheck it, probably contact the authors and whatnot. But I don't think the license change should be a blocker for us to make any progress, right? Because the force fields that we create aren't bound by the same terms of the license as the software. So, when we want to make our toolkit available to, we do want to make our toolkit available to all by changing the license, but that shouldn't prevent us from starting work. It will be important for ForceBalance to be able to read ab initio and experimental data in standardized formats, which I think is going to be very good because, for a very long time, quantum codes have not had standardized inputs and outputs. I think that it'd be really important to have that and to support that. And we should add property calculation codes for properties of interest, including some of the ones that we talked about today, and add some code to carry out MD simulations using cloud resources. And here's some more speculative longer range future developments. So first, I think ForceBalance should be able to optimize the Smirnov 99 force field out of the box. Maybe we, because the strings are a little bit unexpected, I might have to fix the parser a little bit, but probably not anything huge. I'm not sure if there's any benefits for ForceBalance to actually interpret the strings and understand them. Maybe we'll find out in the future that would be helpful.
What about just refactor it? So right now you have a text parser, right? But if there was a way to make that as a plugin module that has an interface that says change this parameter, change that parameter, etc., then you could have just an XML parser that does the same thing, essentially, where you tag certain things with an attribute that means you want to optimize them.
Right. Right now it has both a text parser and an XML parser.
It just uses like LXML?
Yeah.
Oh, okay. So how do you identify which ones you want to optimize then?
You add a tag called parameterize.
So yeah, it sounds like that would be that would work right off the bat then.
Yeah, and then and you can also there's also a fair amount of flexibility in including relationships between parameters because you could allow certain parameters to be mathematical expressions of the other ones.
Oh,
It just uses the exec.
okay. So as long as we're not changing the number of types, then it could just optimize the parameters, existing parameters already.
That is right. Yeah,
Okay.
right. So ForceBalance currently does not allow you to swap to like change between parameter spaces. That would be a more a more major change. I think it may also be helpful in the future to incorporate some non-simulation property estimators, like the kind that that Michael was talking about. And then maybe a few years down the road, I'm not sure what ForceBalance will look like in the year 2020 if all goes according to the way we want. But maybe ForceBalance could implement some of these Bayesian parameterization ideas. So these are just some of the hopes that I have for where to take the code in the future.
Have you considered developing a CUDA version for your program, or is it fast enough multiple times?
The computationally intensive part is in the MD simulation, which is the external, which already uses CUDA. ForceBalance itself does not have to be fast.
But what if I use that to process some very data intensive, like our binding data usually involves a lot of, like when we are computing our derivatives, it involves computing a lot of.
So he has modules that would do the heavy lifting for that sort of thing, right?
Basically, just would spawn off MD simulations on your GPU resources.
Or use CUDA, to
Well, I think,
evaluate them.
if I may, are you referring to processing the trajectories?
Post-processing.
To compute, basically, if you want the derivatives from these trajectories, you've got all these
Those.
lambda windows, they all need to, well, actually, if you're doing free energy,
The
you don't have
endpoints,
lambda windows, you just need the starting and final.
Yeah.
But those need to be processed.
Yeah, but that should be easy to plug in.
Yeah, right. So if you're referring to if the computationally intensive part involves any molecular calculations, that part is just handled by the external code. Like for example, you may need to do a lot of single point energies or single point gradients for getting your parameter derivatives. OpenFF handles all of that, and it would use CUDA if you have OpenFF CUDA.
Silly question though. Do you recompute the free energies after you take a step, or do you just use the gradients to do your descent until the gradient becomes small, and then you reevaluate the free energy at the very end?
I use the analytical derivatives.
The analytical, but yeah. So you compute the derivative, but computing the change in free energy is like if you take a number of steps in
Yeah,
parameter
sure.
space.
If I may, I think you did use the gradient to make a linear extrapolation of what the free energy should be, find a favorable point, right?
Mm-hmm.
It was just a linear.
But you're taking multiple steps, right? You don't just take one step and then you're
It's
done.
only took one step.
We only I did 2 runs, but the second run the derivative didn't do anything because the RMC and the MC are already really small.
So you
Are you asking how to compute the derivatives?
no. So you run the simulations at the endpoint, lambda equals 1 and 0, and then you compute the gradients. That's
Right.
easily doable. It's analytical given your gradient computation of the energies. You propagate that to your gradient in your error metric, right? And then you just extrapolate to error equals 0, and then
You guys want to work through this in a little bit?
yeah.
Seems like we're having to go a little bit deeper.
Sorry.
Leaving is at the end?
It is.
We're going to try another attempt at Vicky's.